Hey guys, so today I'm going to be talking about and demonstrating, another little project of mine. And actually, I'll just first close Steam up here so that's not as large. So basically, um, you know, this one, which you can see as training here, and it's called MNIST it's an autoencoder. So if you don't know what an autoencoder is, we're just gonna do some simple stuff here. I'm gonna show you. So an autoencoder. This is just some searches from when I was trying to troubleshoot some things with regards to this whole thing. I did not end up finding anything on Google. However, I'll get to how I fixed the issues that I had in a minute. So we're gonna go. Sorry about that, architecture for an autoencoder. And let's just take a look at it. So what you can see here, if I just show you this, is that basically the way an autoencoder works is that your input, your target value, is always the same as your target output, right? Or at least in theory it's the same. And what you're doing, right, is you're just taking this and you're essentially reducing its dimensionality until you have a, an n-dimensional vector such that, n is much larger or much smaller than whatever, dimensionality the input and output vectors have. So that's just a simple explanation of it. And what you're doing here is you're training, you're running one neural network, which is essentially a combination of two. And those would be the encoder, so it takes an actual input and converts it to a vectorized, a reduced dimensionality vector, and then inputs that to the decoder, which you can see is labeled here. Actually, I didn't realize that, which produces an output which is theoretically the same as the input, and that one is essentially just. Sorry about that. I'm a bit tired. That is essentially just the output, or that's essentially just an increased dimensionality from this, property vector. And I call it a property vector because essentially the idea is that in theory, if you were to train this well enough and, create a model that's good enough for the given situation, it would essentially learn specific characteristics of this, image or whatever your input, and to use those to come up with a smaller version, so like a compression, and then be able to decode those and create an output from that, and unlike a compression algorithm, the way it would do that is more of like a natural human type of way. So like if I'm a human and I want to store something, some idea in a smaller way, or in a more compact way, or at least deliver information in a with less actual speech, right, or writing or whatever. And I essentially I want to just create brevity. I can describe as opposed to simply I can describe in terms that imply specific things about the object or the situation, and essentially I can take certain characteristics and use those to form a better picture or representation of what I'm trying to convey. Now, with a compression algorithm, you're taking specific characteristics of a data set and using those. However, they're not learned really. They're just deduced through various methods of statistical analysis, and that's not that great. Those are very concrete things, and they don't create exactly the greatest compressions or compression ratios. In deep learning, though, with an autoencoder, you can reduce dimensionality quite significantly and still come out with good, smooth outputs that are seemingly organic, or at least bear a significant resemblance to the input data. So that's what we're trying to do here. Now I'm going to close this tab and come back to this. So I have this running. I've switched IDE, or editors, I guess you could say, to Atom. Because Atom, first off, looks much better. But also, it has this little section here which allows me to actually just stage changes to Git repository. So, just an FYI, I do have a GitHub set up. If you'd like to, check out my past projects on this channel, projects that I'm working on that aren't on this channel, which, none of those are up yet. And also, find code from videos in order to use that as a reference. Check that out, link in the description. But yeah, let's get into this. So, an autoencoder, right, is two neural networks which run, synchronous throughout the training process. And so, what we're going to do is we're just going to create classes. So I'm trying to do this just in order to make my code neat. Obviously, you don't need classes like these, but with the tic-tac-toe thing, it would have just been easier to create an instance of the board as, an object that could be controlled in some way, and then just reset it by creating a new instance and overwriting the previous one. And so we're switching to that kind of, setup for code. So, how are we going to do that? Well, sorry about that. First, we do our imports as usual. Now, there's some differences between this and the previous videos in that we're importing CSV first and foremost. Also, matplotlib's pyplot is being imported as PLT. Basically what we're doing there is just adding something so we can graph specific numbers, and I'll get into the applications of that in a minute. We have a definition for sigmoid, so I decided that during this video we'd use sigmoid as a normalizing function for our inputs, just so that it would be easier for the network to interpret values and come up with a decent output that doesn't need to be, normalized to the, most, the greatest degree imaginable. So that's just why I've done that, so that, the network doesn't necessarily have to normalize everything. This can instead do that, or at least help to make it easier so that we don't come up with, inputs that are 0 to 255 and then everything is, using hyperbolic tangent activation, just completely different. So I just figured this would be easier. So, moving on after that little, rambling of mine, getting past the drivel, we have now our class. So we have one class during this project, pretty simple, pretty straightforward. We have our neural network class. Now, the first thing to know is that this, we're going to, once on initialization of the class, so on instantiation of a new instance, we're going to define our model, so like our full model, which is a combination of the encoder and decoder. So they run in tandem within the self.m variable. Then we have our encoder, our decoder, and then we run this initialization function. So we're going to initialize our neural network. So we're going to sort of use like a flowchart kind of guide to just check out every part of this. So moving into this next step, once an instance is created, we check if the file already exists. If it does, we load the model, and then we can just move on to the rest of this process. But assuming that we don't have one already, just to get through all of the cases, we initialize our encoder. Now our encoder network is just a sequential network with a 3 layers or 4 layers, 1 input, 2 hidden, 1 output, output of 10 units. That's just our our vector size for end of dimensionality reduction, and the branch between our so that's like where we're bridging between the encoder and the decoder would be this 10-dimensional vector. So basically, first layer 400 units, so 400 neurons. That comes from an input layer, which is 784. The MNIST training set is 28 pixels by 28 pixels, so we're just using 784, which is 28 squared. we're just going to, interpret the MNIST dataset as a flat set. Instead of, taking in the 28 by 28 array, we can just take in one 784 by 1 matrix of values. So we can just take in one, vector. And then, as usual, we're initializing all of our weights to be random and our biases to be 0. We're using hyperbolic tangent as our activation for every layer except for 2, which I'll get into in a moment. Now, 150 for the next layer and 10 for the layer after that. This is just a way of quickly reducing dimensionality until we get to our, bridge here. And then we return this. So when this is called, we're going to return it. Then we're going to compile. We're using the Atom Optimizer with a relatively low learning rate. Not too low, though. And then we're running, mean squared error for loss, and we're printing our accuracy as a metric, though that ended up being completely useless. And I'll get, into what the output is in a minute, but it's just strange. And then next, we're going to, initialize our decoder, so we do that down here. Now, we're going to take in 10 dimensions for, those 10 dimensions essentially just correspond to our, 10-dimensional input or output vector for the encoder. The decoder takes in those 10, characteristic dimensions, and that vector is then converted to a 150 neuron hidden layer for the decoder, then a 400 neuron hidden layer, and then a 784 neuron output layer. So pretty standard stuff here. Now, the activation here is sigmoid because I just felt that having, our outputs and therefore our vector be within the bounds 0 and 1 seemed most logical, since just in terms of me being able to then operate it manually later and generate random, values, it's just easier. So that's what I went with. Next, we're going to move on. We're using sigmoid at the end. Because, since we're going to plot all of these values, and we're trying to create image data here, 0 to 1 is what we're going to want. We don't want any negative values, since then we'd have to, use scaling and normalization in order to actually, bring them into some kind of, scale which would allow us to actually plot them. So, I'm not going to get into how you would do that, but it's just useless. It would be redundant to do anything other than sigmoid here. And you'll notice we're not using rectified linear here because it limits us in that, one, our values aren't already normalized, so when we come to the sigmoid function, we're just not going to get as much of a precise result. But also, I really hate using rectified linear when we don't need to, because we have that flat, completely flat portion, which is after when we pass below 0 for our actually below or equal to so once we're at an x value such that we're on the left hand side of the graph, left of the y-axis, we end up with this completely flat line for our, or flat ray, I guess, for our output from the rectified linear function, and it's just not ideal, especially since it's not differentiable. So we're using hyperbolic tangent here. Also, hyperbolic tangent is just good in general. So why not? The only reason we didn't use it for some stuff like the DQ reinforcement learning was because we didn't really want normalization, since we're estimating Q values. That's not really useful in any way. So next we compile this one, same way of creating a compilation as before, and then what we do here is interesting. So we're creating a sequential model for our full encoder autoencoder, I guess, network. I call it the encoder decoder, but it's it's technically an autoencoder. And basically we're going to add the encoder. So this adds this entire framework of layers. And then we're going to add the decoder after that. So it's basically the equivalent of adding a layer. Since these have, since this input dimension value is the same as this output dimension value, we're not going to have any issues. They will transition perfectly. Basically just, sort of snap together, almost. And then all we're going to do is compile this model with the exact same, format as before. And then, next we have one last function here, which is our save all function. And all this does is, it saves the encoder and decoder to the relevant files, deletes both, and then just reruns this initialize neural network function. So pretty simple stuff for this class. Next we have our main section. And basically we're going to have the user select the mode. If the mode is training, we're going to just run this in a loop, and basically the way it works is, so this b value is just essentially set. So basically when we, in this CSV file, the headers are a part of the CSV file, so b just allows us to ignore the first row of the file, and then after that we can start actually, creating training data. So what do we do after that? Well, we take our, we set an array value and an x value to be, so our x value is essentially our input to the network. Our array is the, normalized value, which is what we're using as, so like, obviously since we're putting, our outputs from the, network, from the decoder through a sigmoid function, we're going to need to also put our, target outputs through a sigmoid function in order to normalize them, accordingly. And so that's what we're doing here as well. And that's why we have two arrays. Now, what we're going to do here, or I guess lists in Python, what we're going to do here is we're going to use that CSV, import from earlier to open the CSV file, and then use the csv.reader function in order to read, all of this file. This comma indicates that the separating value between each, that the, I guess it's in the name, comma separated value, CSV. Right, in the CSV file, the delimiter is essentially the separating value between values within the, within each row of the file. So that's basically just what that means. And then, since the b value is initially false, we ignore the first row. And then if we're on the second row, what we do is we essentially take everything past the first value, since the first value in the array, so this is, value 1 and on through the rest of the entire array. It wouldn't take 0 because 0 is the label, which would be, that's essentially the value for the, what number it actually is. We don't need that, since this thing has nothing to do with what the actual identity of the number is. The class doesn't matter. And then what we're going to do is just convert this to a NumPy array with the data type float64. Float64 is important, as opposed to doing like uint8, which would be an unsigned integer, 8-byte maximum, which would theoretically be, 8-bit maximum, sorry, which would, be ideal. We have to use a float because, when we put it through sigmoid, we're gonna have conflicts if we're using 8-bit integers, or at least that's what I found. So we were getting overflow, and that was just destroying our result. So that was one of the things that was why I was in that panic looking that stuff up. But I just had to think for a minute, and once I realized that the issue with the overflow would be because the data types were conflicting with the function, it all came into place, or all fell into place here. So next we append the x values to the image, right? We don't need to normalize these since these are the inputs. Having them between 0 and 255 doesn't actually matter, as it turns out. Next we're going to use especially since we have a hyperbolic tangent as our normalization between layers. It's already going to be normalized pretty early on into the network, so that paired with weights and biases can account for everything with the larger scale for the typical values. 0 to 55 is obviously larger than grayscale between 0 and 1, which is what we're using on our output end with the sigmoids. So then for the array, which is this is our target value array essentially, we put everything through sigmoid. Now our sigmoid function essentially just takes in an array or a single value and converts it to a numpy array containing that one value or just a value. I guess if it's not an array, there'd be no reason for it to be converted to that. And the way, sorry about that, I'm kind of tired again. I apologize. So again, the way that we do that is we just take our array and we put it through that. The reason that it works with an array is that we're using the numpy exponential function within our sigmoid. If you don't do that, it's not going to work with an array or like a numpy array. I don't even think it works with a list otherwise. So moving on, this is just to check. So basically every time the array becomes the array's length gets to 40, we do some training on that batch of 40 10 epochs or epochs. I don't know how you pronounce that still. I've not looked into it. I keep forgetting. And then we reset our 2 arrays. Now the reason we would fit in a smaller batch is just because we'll come up with more precise values. What I found is that if you run it in a batch of say like 60,000, you're not going to end up with anything specific. On the contrary, you'll end up with basically the most generic output it can derive from the data set, and so it just ends up like sort of a clump in the middle with highlights of in specific areas where you tend to see a lot of numbers. Like you'll find a highlight where there'd be like a line upwards. It's like 4s and 1s and 9s all fit into place there. And some outlines like circles. It just looks sort of terrible, and it doesn't change based upon the value that you add. So that's a whole different story. We're not going to talk about that right now. Then we just print saving here. The reason I printed saving is just that we can sort of have like some idea of when this thing is resetting and just looping through again. Then we do this save all function I wrote or I talked about earlier. Next we have some modes. I'm not going to get much into these modes, but basically custom mode allows you to input your own 10-dimensional vector and create a custom number and test out the parameters in order to see what they all really change. Our testing mode is just essentially a way of like, so we basically take in actual values and then we use the full autoencoder network to predict the outputs, just to see like what kind of output we're getting relative to when we have an actual input from the training set. That creates a reasonable vector for a number that's actually been hand drawn. And then the other thing we have is random, and basically this just generates new numbers with random through the creation of random vectors being used in the decoder network. And so now we're just going to okay, so I don't know what this issue is here. Maybe the file corrupted, but anyhow, there are obviously some things that go wrong here sometimes, but you can see like these values are very low. The loss has gotten so low at this point that it's just creating phenomenal outputs, especially for the non-randomized functions. I mean, obviously the randomized, you can't have as much of an expectation for it. Sorry, I'm so tired at this point. Expectation. You can't have as much of an expectation for that. If you're just adding random, vectors, you're not going to get as much out of it because obviously a lot of numbers are very similar. It's not like with, an autoencoder for something else like faces, I guess, or something, that has more of a variety about it. If we're using numbers, a lot of people in the data set draw their numbers in very similar ways. Numbers are meant to be drawn in similar ways. So, the vectors look very similar. So if you give it some vector that has nothing, no relation to really any of the numbers, you're going to get some weird results, and I'll probably show you some of those. So we're going to open our file, and now we're just going to run our script, which is MNIST _AE.py, and, we're just going to run this thing. So for mode, we are going to select I guess we'll choose the testing mode, and testing is just going to give us some output. So you can see this is a 5. So obviously what it's done is it's taken the data set's value and just used that to create its own value. So it's compressed it to a 10-dimensional vector from a 784-dimensional vector input, and then created the output, and this is what it looks like. So you can see we're not really losing much despite this temporary dimensionality reduction, so I'm very happy with the results for that. This is a 0, 4, 1, a 9, 2, 1. So like you can see these are really good outputs. Like I'm actually very surprised by how well this turned out. Kind of stoked about the whole thing. I guess that's a 6, but we can't see the input right now, so it's kind of hard to say, what it actually looked like initially. 7, that's very good. So you can see, these are really good in terms of, like, clarity. They're just above and beyond what I ever expected from such a simple architecture. 2, 4, right? So, that's cool, right? But what about generating random stuff? So we can run this desktop and this autoencoder. I don't know why I do CD every time since I'm literally... Okay, let's just do it like this. Desktop / MNIST _autoencoder / MNIST _AE. I need to stop choosing such long file names. It's getting annoying typing in these paths. Okay, oh, yeah, sorry. See, I always forget. I actually have to navigate to the file unless I'm running it like Python or something. So I'm not very adept at navigating terminals and command prompts. Command line is not my home. So here we go. So we're back in the mode selection screen. Now we're going to choose random. And you can see this is a 6. So this is not an actual. So you can see the label up here. It is actually sampling from the 10-dimensional vector space and using that as an input. So it's sampling from 10-dimensional space in order to come up with new outputs. And, sometimes it'll come up with some really wonky stuff, but also, this isn't from the dataset, so, I'd say this is very good. Pretty straight-looking 6. The only thing that's a bit odd is this branch here, but I'd say, it could be between numbers, sort of. Like, there could be some uncertainty there, so there's certainly that. This is clearly a 0. I see, this is what I'm saying, like, I don't know what this is. Maybe it's a 0, maybe it's like... It sort of looks like it's halfway between like a 0 and a 2. Like you can see, so if I like trace over it, you can see this is like clearly a 0 kind of shape, but also like this could be coming around like that, like as a 2. So I don't know. It's kind of abstract stuff here. But obviously the features that it learns are abstract as well. This looks like sort of like a hybrid between a 7 and a 9. Like it, or maybe even like a 1 and a 9, maybe a little bit of like a 7 kind of shape coming off there, and we have like a line forming down here. They're all very similar, and so I think in the vector space they would be like within a certain proximity to each other. Obviously, I didn't use like 3 dimensions or 2 dimensions for this, so it's kind of hard to do that kind of like plotting of like specific features in order to see like if there's some kind of logistic separability on that, level. If we could like perform any logistic regression in order to sort of separate values and see how accurate this thing is at isolating them to their own specific regions. It's just, it wouldn't be possible, in this case, because obviously humans can't really interpret 10-dimensional spaces or even visualize them, so we're just gonna move on. This is sort of like a slanted O. So what I mean here is like the values that it's inputting are really weird, and so you're gonna get some really strange stuff. Like what even? Why do you have such a large block here? You know. It's like it just, you know, some of it's just sort of like the network has learned these features, and when we deviate outside of like combinations that it would typically see, it just goes insane. That's sort of like an incomplete 2. That's not too bad. That's clearly an 8. So like, you know, a while ago you wouldn't have been able to see that, but I'd say like the accuracy of this thing has definitely improved with more training. I'll have to try running it overnight and see how the results are in the morning. Obviously, we sort of plateaued already, but I think that with more training we can get to a lower value, and maybe I'll restart the training at some point with a plotting function just to see what these loss curves look like, and maybe put those in the README on the GitHub for this thing, so that or you know, on the repository for this thing. Sorry, I'm kind of new to the whole GitHub thing, you know. I don't know a lot of the nomenclature for things. Or sorry, not nomenclature. Nomenclature would be a way of naming things. Sorry, I don't know a lot of like the colloquial expressions or like terminology for various things. I don't know why I said nomenclature there. So you know, we're gonna move on to another number just to show you guys. So this is a 9. I'm just trying to get a variety of numbers so that you can tell. You know what I'm trying to describe here. So this 9 is clearly pretty well refined, and what I'm saying here is like I think that there are certain numbers that are just really perfectly matched in the space with like their categories, you know, like their classes are actually at the point where I think you could probably use like outlier analysis to sort of decipher like what the classes might be here, and like come up with you know, a logistic regression that, you know, actually like sort of isolate specific class types. You know, maybe outlier analysis could work there, as I was saying earlier, but I don't know. I do think it's interesting though. So we're definitely gonna check out another. So you know, this is an O. Obviously there's some weird things branching out here, but you know, the lightest parts are clearly forming an O, or I guess a 0. You know, not an O. It looked more like an O, but you know, these are numbers we're talking about here, so I guess that's actually a pretty funny thing to think about. Like a lot of people draw their zeros like O's, so I wonder if that's actually like if some of the people within the training set actually drew their you know, zeros sort of like how you might draw an O, you know, because that was reminiscent of a 0. However, I don't know if that's just the, you know, the value that we put in, or if that's actually like a learned thing. That's another 0. That one's clearly 0. It's just a bit slanted, as you may find in the MNIST set. This is like a weird kind of what is that, like a weird 8 shape. It's a bit slanted. It's just kind of odd. That's a pretty nice 2. It's decent. 6. You know, and then we got some stuff like this. This is something that sort of vanishes behavior for the most part, but obviously we can see it here again. Basically the issue that we're having is like sometimes we'll just get weird separations here, like even if there were a connection, it looks like the connection towards which it's leaning is right there. That's like, you know, that's really odd. Like, what does that even signify? Maybe, oh, see, I see this part now. That does stand out to me, and we're sort of grasping at straws here, but maybe an 8 like that? I don't know. Definitely a 6. I'm just trying to show you guys some like examples of this. So like there are some weird things going on here, but overall, not too bad. What is that? That's really strange looking. 2. You know, we had some. The O's turn out nicely. I guess O is like the most generic shape you could have. Like, even if there's a bit of a distortion, humans draw, you know, O's imperfectly, so I wouldn't be surprised. And I guess that's why it's so easy for this thing to get away with, you know, oh, you know, it's just an O, it's just a bit weird looking, a little bit wonky. Like with a 2, like, this is a 2, but like I'd say it's not the greatest 2 in the world, despite the fact that it's better than like some of these O's in terms of actually sticking to things. It's just that, like, even if a 2 adheres to like the rules of, you know, technically like what we, you know, would use to define a 2, we're very particular about the shapes. It's a lot of, you know, turns about it. And then this is just another 2, 0, more zeros, some 5s. Some of those data sets a bit weird looking, but you know, let it slide here. So yeah, I mean, I'm not gonna really talk very much. I think I'm just gonna cut the video here probably. I'll link the GitHub in the description to this project, and you know, additionally my other projects are up there. Oh, that's weird. If you turn sideways, this looks kind of like a face. You can see some eyes and a mouth. That's funny. Yeah, so you know, I'm gonna link to some of my projects on there. You know, I'm going to be posting all my machine learning projects and you know, stuff to that GitHub page for you guys to look at. You know, if you're interested in that kind of thing. You know, and hopefully you guys can just learn something from that. I'll try to comment some more on my code. Like, this doesn't have any comments right now. I plan to add some though. So you know, hopefully. Oh shit, that is the weirdest thing I've ever seen from this thing. That is just horrendous. Yeah, so you know, I'll try to present you guys with some of the code on there. I've already uploaded this one to the repository, but you know, on my GitHub you'll be able to find that. It has its own little repository, and it has just all the relevant files. The only thing that's not on there, due to their 100 megabyte you know, size limit, is the MNIST training set, the CSV file for that. I will probably link that in the description if I forget. It's just a Kaggle dataset, very standard stuff. So you know, if you want that, it's just a CSV file, just a few clicks to download it. You know, 100 megabytes or so not that bad. And yeah, if you enjoyed this video, please leave a like, subscribe for more you know, machine learning and programming content from me. Stay tuned for the next video, and don't forget to check out the GitHub page for you know, more information on these projects, you know, how they work, and just you know, a general understanding of machine learning and programming. So yeah, bye guys.